So hi everyone, I'm Sanjay Arora. I work at Red Hat, specifically at Red Hat Research. And I want to talk about learned software systems. So let's dive in. So as most of you know, if you look at system software, operating systems, compilers, cloud systems, they're full of heuristics, which are handwritten rules. And these heuristics guide decision making. So some examples are schedulers in an OS, so in the Linux kernel, schedulers for Kubernetes. If you look at compilers, compilers have a bunch of heuristics that we'll talk about soon. Think of circuit design or combinatorial problems, optimization problems in general. They have a bunch of heuristics too. And then if you crack open an OS, it has heuristics for very specific subsystems. So for example, the NIC, the network interface card, has a heuristic for what's called the interrupt delay. Or CPUs have heuristics for dynamic voltage and frequency scaling. It's called DVFS. And imagine you had to write a heuristic. What would you look at? So you might want to optimize something. You might want to optimize performance. You might want to optimize resource consumption. In general, it's not possible to optimize everything you want to. So there'll be some trade-offs, and you have to make them in a judicious way. And the important thing is if you write heuristics in a lab on some workloads, on some hardware, they ideally are generalizable. So if you deploy this, you push it out, and suddenly your system sees a workload it has never seen before, it shouldn't catastrophically fail. It might not be optimal, but it should at least perform decently. And there's a term which is not very creative. It's called ML for systems. And that refers to finding better heuristics using ML techniques. Okay, so finding better, instead of handwritten rules, can I find better rules for a system using some machine learning techniques? Now, if you want to do this, you need some infrastructure. And you broadly need two things. You need to be able to observe what your system is doing. So that involves several metrics and frameworks. So for those of you who are familiar, frameworks like eBPF are great for this. There are various tracing technologies that access low-level hardware counters, for example. So you need to observe your system carefully. And you also need to be able to intervene in your system. You need to be able to change it. So there are, again, various quantities that you can tune or manipulate. So you say, OK, I want to learn heuristics with machine learning. And I have some metrics I'm going to observe, and I'm going to go and change a few knobs. But where do you start? So there are two types of problems. First, on the system front, you need to identify what subsystem you're going to work with. You're going to identify what metrics you're going to collect. How will you observe the state? And this is tricky, because you ideally want to observe everything, but you don't want large overheads. You don't want to change how your system behaves just by observation. Then you also want to pick the knobs that you will tune. How are you going to intervene? And that takes substantial system expertise. And even if you get all this right, then you need to make careful measurements. And in our experience, most of these problems where you're applying machine learning to optimize a system fail because the measurements aren't done carefully enough. It's very easy to get a lot of noise. So controlling the noise in the system, doing the right type of cleanup. So when you do repeated measurements, you're actually getting independent measurements. All of these are crucial problems on the system side. And then there are a bunch of statistical and machine learning problems. Maybe the primary one there is the question of sample efficiency. So if you run experiments on a machine, they can take several seconds to even several hours or days. Large benchmarks can take a long time. And if you have some technique that needs thousands of evaluations or hundreds of thousands of evaluations, that's never going to work. So sample efficiency is extremely important, and that often governs the type of techniques you'll use. And then there are specific questions like, the scalability of techniques when it comes to the number of knobs you're tuning, the kinds of the amount of noise you have in your system. There's some techniques that really want you to sequentially do measurements instead of parallelizing measurements. So those are the kinds of questions that one has to address, but this is still a bit too abstract. So the main takeaway is you can't just throw machine learning at systems problems. You need to really understand your system and carefully design your experiments. So instead of talking abstractly, let's look at one specific example. This is joint work between Boston University, so Professor Jonathan Apawa's group, and Red Hat. This is Han Dong's thesis work. And the setup is very simple. So you have this stack, you have the hardware, you have some OS running on your hardware, and you have some application. Here there's an application called Memcached. And essentially you have requests coming in from the outside world, which is the external load. And your job is very simple. Requests come in, you do some computation, and you return an answer back, and you have a time limit. You have a time limit in this particular case of 500 microseconds, half a millisecond. To be more precise, it's the 99th percentile latency. 99% of your requests should go out in half a millisecond. So very simple setup. Someone's asking you questions, you have to answer within some time frame. And the question is, can I do the same work while minimizing the amount of energy that my system uses? So you say, okay, what can I control? Now, there are many things you can control, but let's pick two things. One thing I can control is as requests come in, I can ask them to queue up. I can say, I'm not going to serve you right now. Please stand in line. And then at some stage, I, as the system, need to decide when to answer your query. And the other thing you can control is your processor frequency. So you can slow your processor down. You can say, everyone, please queue up. I'm going to slow my processor down. It's not doing any work anyway. And then when I'm ready, I can wake it up and start doing the work. And so we said, well, let's control these two mechanisms. Let's ask request to queue up. That's controlled by a knob called ITR, or interrupt delay. And let's modulate our processor. That's through that knob called DVFS. And these are two very busy plots, but let's deconstruct them. The x-axis is the same on both of them. The units are different, but it's the same. It's 24 hours. The y-axis on the left plot is the energy consumed by the system. The y-axis on the right one is that latency. How much time did I take to respond for the 99th percentile? And if you look at the two curves, two plots, they both have a red curve. It says QPS, that's queries per second. How many requests are coming in per second? So as time goes on, through the day, the number of requests you get varies with time, which is natural. That actually reflects a real workload at Twitter. Well, I should say X now. And you can see the blue dots on the right side. That's the latency that Linux performs at by default. So by default, even though you need to respond to requests in 500 microseconds, Linux tries to minimize that. It responds in 100 microseconds, so much faster than you need to. And on the left side, the blue dots again show you the energy consumption on Linux by default. And of course, without having some intuition about this, one doesn't know if that's high or low, but it's pretty high. So you're responding very fast, but your energy consumption is high. And so a natural question is, can I maybe respond a bit slower? Can I maybe pay a price in latency, but reduce my energy consumption? And so we tried that, and on the right side, you'll see the green stars. Those latencies are when you tune ITR and DVFS, the two knobs you have, to their optimal settings. And what you see is they go up, latency goes up, but it's still within the limit that you need to have within 500 microseconds. But on the left side, you see a dramatic saving in energy. The green stars go down compared to the blue dots. And in some cases, you get something like 40, 50% energy savings. So if you zoom out, even if you forget the details of what I said, The main takeaway is just by carefully designing your experiments without changing your application, without changing your operating system, by changing just two knobs, you can get dramatic savings in energy by trading off some latency. And this story repeats across all system software. You have a lot of room for improvement without really rewriting any code, just by changing the knobs that are exposed by developers. Another example, and I won't go through this in detail, is compilers. Compilers have something called optimization passes or phases. They take code and transform code into other code, and they do this in the hope of making the code more performant. All of this is automated. It doesn't change the meaning of your code. The effect is the same. And a natural question for compiler writers is, I have all these optimization passes, so imagine n optimization passes, and you need to apply them to your code. And the order in which you apply them matters a lot. That can have a big impact on your code performance. So a natural question is, what order do I apply my passes in? And I have a link to a paper where we use reinforcement learning to try and learn that. And again, depending on the source code, you can get significant performance improvements. And as before, you're not rewriting your compiler, you're not rewriting your application. These are all existing capabilities in system software where you have potentially huge improvements in resource consumption and in performance. And the price you pay for it is you now have to use some machine learning to try and find these solutions. I can't say anything about ML without mentioning large language models. I'll probably be fired for doing that if I didn't mention LLMs. No one can deny that there have been huge advances in LLM capabilities in not just the last year, but the last 5 years, last 6 years. And these are no longer just LLMs. They are multimodal models. They can process text, speech, so audio, video, and text also includes not just human text, but code. And so we have tried these for a few problems which are not traditionally systems problems, so problems like generating unit tests. And while you do need to manually tweak what comes out, and you need to filter the results, they are extremely promising so far. Now, there are a few papers that claim that their LLMs are great for combinatorial optimization. I personally don't think these are replacements for, let's say, reinforcement learning or Bayesian optimization. But when it comes to code generation, they can be extremely powerful. But like Jeremy said, when it comes to system software, like kernel code, you want to be a bit more careful. And lastly, I'll just summarize what I said and give you a sense of what we are working on at Red Hat Research. So the main takeaway is that even with existing software and existing hardware, there's a lot of room for improvement by tuning systems without rewriting any code. And most of these experiments, when we have seen them fail, they fail because of bad design of experiments. So it's very typical to set up some experiment, throw some ML at it, say it doesn't work, right? It doesn't find any solution. And as an example, I remember once looking at someone trying to tune one parameter, and they said, oh, I can't find a better solution. So we said, let's do a brute force search. And there was so much noise in the measurements that the noise was basically washing out any differences in the tuning parameter. So you can't just throw ML at it. You do need to design the experiments carefully. And these are, of course, not all the projects we are working on, but we are trying to extend that NIC tuning example with ITR and DVFS to noisier settings in OpenShift. So what happens when you have OpenShift or Kubernetes running and trying to allocate pods to resources, to hardware? We are also doing something that's a bit more experimental, where instead of learning a large language model for code, can we learn a large graph neural net on code? So instead of looking at code as tokens, as text, can we look at code as control flow graphs and data flow graphs? And can we, just like LLMs, in a self-supervised way, scale the training up to learn very good embeddings or representations of code? So that's an active area of exploration at Red Hat. And of course, we are working a lot with compilers. So not just ordering of optimization passes, but can we automatically insert pragmas into code? Can we pass the right command line arguments? Yeah, hopefully we'll make progress over that, or on these problems over the next year. But if there's one takeaway, that is that if you look at the machine learning community, we focus a lot on computer vision, on natural language processing, on video processing, audio processing. Those are great problems. I would like to add one more to that, which is machine learning for systems. There's a small growing community around this work. There's a workshop every year at NeurIPS called ML for Systems. But we definitely need more people to work on this, and we need more systems researchers to work on these problems. So that's all from me. Thank you. Any questions? I'll be around too, so if anyone has specific questions, please just come and talk to me. Otherwise, I think we have a break. Question? Oh, please, yeah.
Yeah, when you're making the trade-offs like the power and the latency,
Yeah.
Is it reasonably well established how to reason about like layers of application? Like if the system service is increasing the latency by this much, and then there's an application layer and another layer, middleware and so on. Is it reasonable? Are there now ways to reason about that kind of end to end to know what the final application gets? Or is that really still just a matter of art and people just have to try it out and see how bad it gets or how good it gets?
So at least for us, the latency measurements are across the whole stack. And it depends, right? So that comes back to the question of what state are you measuring? When we were doing this problem, we were treating this as a black box. So there are specific black box optimization techniques like Bayesian optimization, which say, can I, in a sample efficient way, if you do accurate measurements of latency and energy, find the optimal ITR and DVFS. If you do have some fine-grained profiling or tracing, then one could absolutely say, you know, I would like to, for example, minimize the latency in this layer. I don't care about the other ones. I don't know if that's exactly what you're asking. I'll add one more thing. All of these techniques do let you characterize the trade-off between energy and latency. So you can actually answer the question, if my latency is 100 microseconds, you can quantify statements like the following. I can increase my latency by 2%, but I'll save 5% energy. So you can get these trade-off boundaries, but they are in aggregate across all the stacks, across all the stack.
Hi. So one of the things I love about that work is that it shows the value in customizing and tuning the environment for the application running on it.
Yes, yeah.
And if you look at some level, what we've done with Kubernetes and OpenShift is we've sort of said, yeah, kernel is just a commodity. You know, we're running all these different applications on top of it and just looking at scheduling at the high level in terms of packing these things together. These things seem in conflict with each other, are they?
So I know there's a lot of work on customizing system software, like the unikernel work. And there is always, so again, from a mathematical perspective, there's always going to be more potential improvement if you optimize or tune across the stack, right? If you do it layer by layer, that's a local optimization, but not a global one. So ideally, you would do it across all the knobs. And there are open challenges that we have. For example, if you were to list all the Kubernetes knobs, all the kernel knobs, and there are thousands, and if you said, OK, now go and do something, that's troublesome from a machine learning perspective. There are too many knobs, they're correlated in their effects. So we are forced to retreat to one layer at a time right now. But eventually our hope is we'll do exactly what you're saying, which is you say, okay, look at the whole stack, optimize across everything. But that will take a few years probably.